So according to our electromagnetic wave theory, it was unable to explain the concepts of blackbody radiation as well as photoelectric effect. So it was Max Planck in the year 1900 who put forward the theory called as Planck's quantum theory, and this was extended by Einstein in the year 1904. So there were certain postulates. The first one is radiant energy is emitted or absorbed not continuously but discontinuously in the form of small discrete packets of energy called as quanta. So in according to the Planck's quantum theory, energy is not absorbed continuously. It is absorbed or emitted discontinuously, and he called these as in the form of packets, teeny tiny packets, and these were called as quanta. And the energy, the quanta in light, the quantum energy is also called as photons. So the second and the one very important thing over here is that he actually quantized this particular particle, and the energy of each quantum is directly proportional to the frequency. So E is directly proportional to mu, that is the frequency. E is equal to h mu, and h is the proportionality constant, or is also called as the Planck's constant. And the value of h is 6.626 into 10 to the power minus 34 joules second. So here, as you can see, that the quantum is actually, this particular value is quantized. So E is directly proportional to mu, that is the frequency. The third postulate is the total amount of energy that is emitted or absorbed will be the sum whole number multiple of quantum. So it is always a the total number of energy is always going to be a whole number multiple of quantum. So E is equal to NH mu. Okay, from here we got to know that E is equal to H mu. And because we are saying that the whole number multiple means that value, we're considering it as N. And we know frequency equals to C by lambda. So we're merely substituting the value of frequency, and you get the answer as NHC by lambda, where N can be any integer. So basically, the total amount of energy, this is always going to be a whole number. So this total amount of or total value can of n. I'm not talking about the value of energy, but the value of n. It has to be a whole number and it cannot be a decimal. So I can't have the energy, the value of n being 1.1 h mu, 2.3 h mu. No, the value of n is always going to be a whole number. So it's 1, 2, 3, or so on. And based on the above relations, you can notice that the frequency, higher is the frequency, the photons will become more energetic. If you remember, the issue with photoelectric effect based on the Planck's quantum, sorry, based on the classical mechanics, would they did not explain that why is there some amount, the dependence of the kinetic energy of the electrons on the frequency. So as you can see, based on the relation, higher is the frequency, the photons are more energetic. And obviously, these photons will have a high energy, and that's why I will get to that anyways. Point is, the amount of energy is given as NH mu, where N is going to always be a whole number integer. So explanation of black body radiation. So according to the Planck's concept, you have when you have a solid substance, when it heats, as you if you remember, that's what we gave as an example. We took the example of iron, and when it gets heated, it changes color. So what happens is when the frequency is increasing, the atoms are going to start oscillating. And when it's continuously heated, there is a lot of energy that is getting absorbed, and the radiation is emitted at a higher frequency. So here you have um, red has a lesser frequency compared to yellow. So first the emitted light is in the color red, and then it moves to the color yellow, and then you had white and then blue. So all of this is because as there is more energy being absorbed, radiation is emitted at a higher frequency. So this was the explanation of the black body radiation. The second is photoelectric effect. It was Einstein who actually explained the concept of photoelectric effect based on the Planck's quantum theory. So when you have a photon hitting the metal, Electrons are ejected instantaneously. This is something we know. And so here, if you see, the energy of the striking photon is equal to the binding energy plus the kinetic energy of the ejected photon. So the energy of the striking photon, as in that will be again dependent on our frequency. We learned that the frequency, higher is the frequency, more energetic is the photon. So assume we have the energy of the striking photon has h mu. Okay, forgive me for my handwriting. Anyways, so the binding energy, let's consider it as x, and kinetic energy plus ke. Okay, so the value of x, that is the binding energy, it depends upon the ease with which that particular element can lose the electron, right? So when a photon hits a metal surface, some of it is getting used for removal of the electron from the metal, and the remaining is getting used up for the kinetic energy. That is why, if you remember, we stressed on the point that the frequency, if there is a high, if the value of frequency on the metal is higher than the threshold frequency, then the kinetic energy of the electron will increase. So the kinetic energy, the remaining part, that is, so some amount of energy is required as the binding is required for the overcoming this binding energy, and the remaining will get used up for the kinetic energy. So assumption, let's assume that the binding energy is h mu naught, because we know that the mu naught is going to be the threshold frequency. This is into half mv square kinetic energy. So this is why we get the equation. So this is why we get the equation h mu is equal to h mu plus half mev square. I'll just erase this. Um, So what I'm trying to point out is the fact that when there is amount of frequency mu that gets hit on the particular metal surface, the energy of the photon is getting used for two things. First, it gets used up for overcoming the binding energy. If only because it is getting used up for this, will the electrons get ejected out in the first place. The remaining energy of the striking photon is getting used up for the kinetic energy of the ejected photon. And that is why the frequency is what dictates the energy or the kinetic energy of the photon and not the intensity. This was one of the issues of our electromagnetic wave theory, which it could not explain the fact that the frequency is what dictated the kinetic energy of the ejected electron. I'm so sorry, this has to be electron. So kinetic energy of the ejected electron. So So the above equation explains the experimental observation. If the frequency of radiation is less than the threshold frequency, no electrons will be ejected, irrespective of the intensity of the radiation. So here, if you remember, energy is equal to the binding energy plus the kinetic energy. So if the energy of the striking photon is going to be less, it's not going to be equal to the threshold energy, that threshold energy, then obviously electrons will not be ejected out because the threshold frequency will not have enough energy to remove the electrons from the metal. The second one, the frequency of striking radiation is more than the threshold energy. So the excess energy is imparted to the ejected electron as the kinetic energy. This is exactly what we studied in the previous slide. So when it is more, when the frequency is higher than the threshold frequency, the excess energy that is present is getting used up for the kinetic energy of the electron. Next one, each photon ejects the electron. So when the intensity of light is increased, the number of photons striking the surface increases and the kinetic energy remains the same, but the number of electrons ejected increases. So let's assume you have if on the surface of that particular metal, we are increasing the intensity of the radiation. We are not increasing the frequency. We are leaving the frequency to the threshold frequency. but we are increasing the intensity, then the number of electrons is increasing. That is what was observed in the photoelectric effect. And this is because one photon ejects one electron. So if the number of photons increase, the number of electrons will also increase. But notice, because we are talking about it being in the threshold frequency, the photons being in the threshold frequency, the kinetic energy of the electron stays the same, but the number of electrons increases. So in a nutshell, there are only three things that you need to remember. First, threshold frequency. Threshold frequency is the minimum frequency that is required for the removal of electrons. Point number one. So this threshold, so a frequency, when it hits, and if this frequency is more than the threshold frequency, then some amount of it gets used up for, that is up to threshold frequency or threshold energy. Let's take it as threshold energy, that is used up for removal of the electrons, and the remaining excess energy is used for kinetic energy. And that is why when the frequency of the electron is increasing, then the energy or the kinetic energy also increases. The next one, the next one is each photon ejects an electron. So the intensity, the number of electrons, when it has to increase, the intensity of the radiation has to be increased. So when there is an increase in intensity of radiation, then the number of photons, sorry, the number of electrons increases. So intensity dictates the number of electrons, frequency dictates the energy or the kinetic energy of the electrons. So all of this led to the conclusion that when light is regarded as waves, it explained the concept of reflection, refraction, and diffraction. Einstein regarded light as particles. It helped explanation of photoelectric effect and black body radiation. And in the end, they realized that light behaves like both particles and waves. And this is called as the dual nature of light. So light can act as both particles as well as waves. This was what was concluded in the end. So in this video, we learned about the Planck's quantum theory and its postulates. The second, we learned the explanation of the concepts of black body radiation and photoelectric effect using Planck's quantum theory as to how it landed up making these concepts clear. The third, we learned about the dual nature of light. In the next, I think we will be doing a few in-text questions based on these concepts, so do check it out.